works.
Yeah.
Okay, there you go.
Okay.
Okay, ready.
So let me stop the camera. Okay, here you go.
The chat.
You can close it with the X. La X es a la derecha.
To the right.
Okay.
Okay, great. Okay, well, thank you very much to Ravi for the invitation. Like you said, I'm relatively new here in the department, and I'm very happy to have the opportunity to talk about my research, and also to find that there's a common theme in the last few talks of the colloquium with my current interest. Okay, so today I'm going to talk about periodic homogenization of the principal eigenvalue of second-order elliptic operators. And this is joint work with Gonzalo Dávila from Universidad Técnica Federico Santa María in Valparaíso and Erwin Topp at Universidad de Santiago de Chile in Santiago. So, I'm going to start with some, say, introductory material. I apologize if somebody is more of an expert in the subject than I am, but just if somebody is not familiar with the subject, so they can get a little bit more of the talk, right? So we begin by studying or by addressing the connection between optimal control problems and Hamilton-Jacobi equations. And this is a classic topic which gave rise to the theory of viscosity solutions for Hamilton-Jacobi equations. So consider a dynamical system given by an ODE, which you have here, first order system where x dot denotes the time derivative, and it is equal to a certain drift, which depends on the state and also given control alpha. We have right there, and subject to an initial condition, which is a point in a bounded domain in Rn. Right? So the function b is our drift. Alpha is a control, something we can choose, right, to influence the system, and it's taken in a given control space, which is generally some compact metric space. Subject to this dynamics are we aim to minimize a certain cost function, and this is the optimal part of the control problem. So we have a certain function f, which gives us a running cost, a cost we pay as the system evolves, and g, a cost which we pay when we exit the domain. Okay. Another parameter we have right there is tau, which is called the first exit time of the domain. So the cost is going to keep going until we exit through the boundary, and that happens at time tau. When that happens, we stop paying f and we pay g. Okay, and note that the trajectory and the exit time depend on the control. We influence the system in that way, right? So something called the dynamic programming principle tells us that the value function, which is the best possible outcome, the least cost that we pay for the evolution of the system, solves a certain PDE, right? And this PDE is called the Hamilton-Jacobi-Bellman equation, which is the operator defined below, right? It is by some sort of duality, it is the supremum over the possible controls of minus a drift times our gradient plus lambda times, I didn't mention lambda, it's a certain discount factor as time evolves, times the state variable, which stands for u, minus the running cost. Okay? So the the benefit of studying this, say, higher level problem of finding U is that once we find the solution U by whatever means we can in the PDE point of view, we also have techniques to construct an optimal control. Right? This is a classic topic, and I recommend books on the subject by Guy Bars, also Fleming and Sonnet, and even in classic PDE books by Evans, there's a great chapter on this. So, sorry, the notion of solution we need here is so-called viscosity solution, because in general, the function U defined as a cost is not going to be smooth enough to justify having that first derivative. So, a brief word on viscosity solutions. It is a weak notion of solution, but having, let's say, if the usual weak notion of solution, which we use for problems in variational structure, if that is based on the integration by parts formula, the notion of viscosity solution is based on monotonicity or the maximum principle, right? So the definition sort of has to do with that. So we'll define subsolution and supersolution. For example, a function U is a subsolution if, in the viscosity sense, if when touched by a smooth function by below, which we express by saying that U minus phi, where phi is a smooth function, where U minus phi attains a local maximum, then the function phi will solve the corresponding equation, will be an actual subsolution in the classical sense. And the same goes switching the inequality for supersolutions. So as you can see, it has to do with order or monotonicity. Right? Okay. So actually, I sort of got ahead of myself, and I'm writing the sort of definition of solution now for second order equations, whereas the first equation we saw was a first order equation under certain assumptions, say for second order equations. Right? So let's now begin to talk about homogenization. Now, suppose we have a system like the one we had earlier, but depending on at least part of the system, depending on rapidly moving variable, right? Which is x over epsilon for a small parameter epsilon. And to compensate, say, this rapid movement, we assume that the drift p is periodic in this variable. So we can also write, we can just say it's periodic, or we can also write that b is defined in omega times the flat torus Tn times the control space, right? So a possible interpretation, or something to make this a bit more clear, is that suppose we designate this rapidly oscillating variable by y, defining y equals x over epsilon. Now, just taking the derivative, right, by the chain rule, we find that y dot is equal to the drift b in xy divided by epsilon. So if we couple that with the original system, we see more clearly that we have a dynamical system where one part moves a lot quicker than the others, right? Because that drift in the end is giving like a velocity for the component y, right? We see two parts evolving at different time scales, and this behavior found in some real world applications, which I'm not too familiar with, right? But, in electrical circuits and stuff like that, we find this type of behavior. Okay? So, of course, if we repeat, say, the argument of the dynamical program principle, now we have that the PDE, which is satisfied, right, by the value function, now also has this dependency x over epsilon. And it depends on for uppercase f, we have f of x, x over epsilon, u epsilon, and du epsilon equal to 0, and u equal the boundary condition g as before. Now we denote the solution by u epsilon because for each parameter, say each fixed parameter, we're going to have a different solution, say for our PDE. So we now have a family of solutions. Very well. Second order equations, like we saw in the definition of the viscosity solutions, arise from considering stochastic optimal control problems, where the underlying dynamics of the system are given by some stochastic process, xt, and also our control space, our control, is a stochastic process, and the dynamics incorporates a term which accounts for Brownian motion coupled with some dispersion matrix, which, disclaimer, I'm not too familiar with the stochastic calculus, but again, when we run the dynamic principle argument again, this dispersion matrix shows up as more commonly known diffusion matrix, multiplying the second derivative of our solution u in the formula we see below, right? Where we see that f, the operator which gives the PDE, is now the supremum of linear operators, where the leading term is trace of a times x, and a is, in a certain sense, the square of this dispersion matrix. So that's a motivation for second order equations, or at least one motivation for studying second order equations in this context. Okay, so the problem of homogenization in general is to determine the behavior of solutions, of the family of solutions, u epsilon, as the parameter goes to 0. In particular, to see if this converges to something, and to identify that something commonly as a solution to a given problem. Right? Of course, in different contexts, in the context of weak solutions, that theory actually precedes this one in the context of Hamilton-Jacobi equations or equations in non-divergent form. There is a whole different set of reference there. But for the viscosity solutions approach, the main points of the theory, let's say, are contained in classical works by Lyons, Papanicolaou, and Varadhan in '86, a very famous and curiously enough unpublished work, and other papers by Evans, from the author of the famous KDE book. Right? Okay, so what is the idea behind the viscosity solution approach? Motivated, might be, it's going to require some imagination, but motivated by the computation we did, where we saw two different timescales, right, of evolution within our system. We're going to say freeze everything in our equation, or part of our equation, which depends on, say, the slow variable x, and focus on the oscillation with respect to the fast variable. Now, what this means concretely is to consider a problem for fixed x, r, p, and x, which stand for, x, u, the gradient of u, and the second derivative of u, respectively. We're going to freeze that and consider the problem below, f of x, y, r, p, second derivative of v plus x in the torus, in the flat torus, which say is 1 unit of movement for the fast variable y. We're going to consider a PDE, a stationary PDE, where the, say, live variable is the fast variable y. And this is known as a cell problem, or also an ergodic equation, or an additive eigenvalue problem. And this last name is quite descriptive, because the unknowns of this problem are going to be both the function v, we see here, the solution, and a constant c, known also as the ergodic constant, which together form a solution pair for the equation. There exists a unique constant C such that that problem has a solution V also in the viscosity sense, right? So notice that this constant C, this unique constant C, depends on the frozen parameters x, y, or not y, sorry, x, r, p, and x, which stand for the state and derivatives of a function u. So this allows us to define an operator, bar f, or f bar, which depends on these frozen parameters equal to that unique constant C, which gives us the solution of the cell problem. Now we call this the effective Hamiltonian, and it will be, in the end, our averaged problem, or our behavior, the problem that gives us the behavior of solutions as epsilon tends to 0. Right? Now, the motivation I wanted to I think I missed one slide, and I wanted to do this on the blackboard, but I don't think I'm going to be able to do it right here in the presentation. So let me just move my hands a little bit more. And the particular form, if just one quick observation, what happens in the cell problem right there is that, in contrast to the original problem, say the f, which depends on, say, u, the gradient, and the second derivative, the cell problem only depends on the second derivative of v with respect to y. And the thing is that is, in some sense, the part that we cannot control when we try to pass to the limit, in some sense, in the previous equation, right? If we try to, can I try one thing with board? Okay. So, sorry for the technical problem. I need to be able to use the board. One thing.
So place the computer here.
Right, is what I'm trying to. Let me see if that shows up on time. Let me just. Okay, we assume that our function, the function of our oscillating problem, can be somehow decoupled into, say, a slow-moving part and a rapidly moving part, right? We propose this like guess or ansatz, right? Look at this. There you go. Okay, that's how I'm going to do on the board. But I missed writing that. So when we compute. I think that's good enough. So when we compute the, okay, I'm going to try to do a little more. When we compute these derivatives, see, here we have an epsilon. Of course, we have an epsilon here, but for the second derivative, say these terms are of equal order, right? So this somehow disappears when we pass to the limit in some sense, but this we cannot control. So since we cannot control it, we say that it is equal. We say that it is equal to a constant, and get rid of the oscillation that way. So that's the motivation for that definition. I hope it helps. Okay, so closer to our setting. Let's talk about the principal eigenvalue problem, right? So we consider, as before, second order equation f, which given by f, where f satisfies an ellipticity condition stated here below, right? which is basically a monotonicity. It looks a little bit technical, but it's basically a monotonicity with respect to the second derivatives of the problem. Right? Those inequalities give us some sort of monotonicity with respect to the second derivative of the function. Right? And the ellipticity constants, and this is a uniformly elliptic operator, because we can bound this difference above and below by some extremal operators, small lambda and lowercase lambda, uppercase lambda, as written there. So we have some sort of uniform ellipticity condition. That's our first assumption for F. And we also assume that F is positively one homogeneous in its last three variables, which stand for, say, u, the gradient of u, and the second derivative of u. Now, with these assumptions, with these two assumptions, for each epsilon, each small parameter epsilon, the operator f epsilon, right, which stands for the oscillation given by x over epsilon, has a principal eigenvalue. That is, there is a solution pair, u epsilon, lambda epsilon, a continuous function and a constant, such that we have f of, say, u equal to minus lambda epsilon u in omega with homogeneous boundary conditions. That will be our oscillating problem, which depends on epsilon. There you go. So, properties of this eigenvalue is that of the principal eigenvalue is that it is unique in the sense that any other eigenvalue, well, first, it is unique in the sense that every other eigenvalue is associated to an eigenfunction that changes sign in omega and is larger than this principal eigenvalue, and it is simple in the sense that the space generated by the eigenfunctions is one dimensional. So any positive solution will be unique, save for a multiplicative constant. It can also be characterized by an extremal characterization as the supremum of, say, lambdas, such that there exists a subsolution to the problem on the right. There exists a positive subsolution to the problem on the right. And we mentioned that for nonlinear f, or fully nonlinear f, we have been discussing, it is also possible to define, say, like a dual eigenvalue characterized in the same way, but for negative eigenfunctions, right? And these in general will be different, but with respect to this problem, the analysis is more or less similar, so we will focus only on the eigenvalue defined by the formula above. Okay. So in the fully nonlinear settings, these results are contained in papers by Alexander Klaas and Sirakov, and also Armstrong. And this follows or extends the work of Berestycki, Nirenberg, and Varadhan in the seminal paper for linear operators in non-divergence form, where the eigenvalue is actually defined as the characterization above, and then all other properties stem from that. Okay, so a common problem a common feature, in this approach is that the average operator can be shown to inherit a series of properties from the original one. For example, uniform ellipticity with the same constants, same modulus of continuity, And here the homogeneity. It's not difficult to show that using the, say, the cell problem, which defines the effective operator, effective Hamiltonian F. In this case, this implies, all these properties imply that F also has an eigenvalue. F is defined as the ergodic constant in the cell problem, but given its properties, it also has a principal eigenvalue associated to positive eigenfunctions, and this eigenvalue shares the same properties. It is unique, simple, and it has a similar characterization to the one before. So that's, say, the setting of previous results, and now we move on to our results. And the first of these is, say, a general convergence result, which is also known as homogenization. Homogenization is sort of the topic, the problem, but it's also the solution. When the following happens, we say that homogenization occurs. That's hence the title. So, assuming F satisfies the assumptions of ellipticity and homogeneity, we have that the principal eigenvalues of the oscillator problem converge to the eigenvalues of the average operator, and well, U, as I said, is defined up to a multiplicative constant, but if it is suitably normalized, for example, normalized in the L infinity norm, that it also converges to the corresponding eigenfunctions. And where the eigenfunction for the average problem is also normalized. Otherwise, it won't match. So, as far as we know, results of this type. I'm sorry, there's a typo there, but results of this type date back to the work of Quesada, where the entire spectral decomposition of a self-adjoint linear operator is homogenized. In that paper, we have a convergence result for each of the eigenvalues of the operator, not only the principal one. Right? And a quick observation is that in this convergence result, or in this homogenization problem, we have, in some sense, we have more than one scale operating at, let's say, more than two scales operating at the same time. Because we have the slope variable, we have the fast variable x over epsilon, and we also have this coefficient lambda epsilon, whose rate is another unknown of the problem. We don't know if there's a modulus of continuity. We don't know how fast that convergence, as opposed to, say, the other coefficients. We have more information. So this, in some sense, is what is known as a multiscale homogenization problem. A good reference for which is the work of Alvarez and Bardi, not only in that paper, in a series of papers. Alvarez, Bardi, and I believe that one is by Marchi, Camille. No, I'm sorry, Marchi, Claudio Marchi, I believe. And in contrast to, say, other classical problems in homogenization in the viscosity solution theory, here we have what is called a resonant problem, which is not, say, strictly, we don't have a strict monotonicity with respect to the state variable, right? As we know, once we have a coefficient crossing the value of the first eigenvalue of the principal eigenvalue, we can have loss of uniqueness, etc. So in this case, we don't exactly have the series of comparison principles or maximum principles which we normally have in the viscosity solutions, say in the standard part of viscosity solution theory. But these principles are replaced by the simplicity of the eigenvalue, the properties we know for the eigenvalue. So that's the first of our results. The second result is that once we have convergence established for both the eigenvalues and the eigenfunctions as epsilon goes to 0, a natural question is to try to find a modulus of continuity, to try to estimate the difference in value in the case of the eigenvalues, in some norm for the eigenfunctions with respect to epsilon. Right? And as of this moment, this work is pretty much ongoing, right? As of this moment, we only 100% surely we only have really a rate of convergence for the eigenvalues for linear, smooth, and autonomous operators. That is, whose coefficients do not depend on the slow variable x, only on the fast variable. So when they are averaged not to functions of x, but to constants. Right? So we'll write this in more detail. Right? So given smooth coefficients, like I said, which depend only on the fast variable x over epsilon, or later y, we have second order operator, linear operator in non-divergence form, given by the trace of a times second derivative of u, sorry, b times the gradient of u for drift term, and for state term c times z, reaction term. And there, yeah, the first product denotes the trace of the actual product. So we consider the principal eigenvalue as before. We have that the previous homogenization result for this problem as well, showing that the eigenvalues and the eigenfunctions converge to a solution pair of the problem there, the principal eigenvalue problem there for the effective linear Hamiltonian L bar. And also we can explicitly average the coefficients A, B, and C. At this moment, that might be not so relevant. Okay, so regarding this problem, we have a linear rate of convergence if lambda epsilon and lambda bar L denote the principal eigenvalues associated to the oscillating problem and the effective problem, respectively, then the difference lambda epsilon minus lambda is bounded by a linear function of E, c times epsilon. Okay. And something which is slightly different than the corresponding results in Quesaban is that here we are, at least with our techniques, we are able to sort of decouple the rate of convergence of the eigenvalues from that of the eigenfunctions. The results of Quesaban, they are, say, more mixed up. Okay, so very briefly, I'm going to discuss some ideas in the proof, right? So for the general convergence result, the first part is a convergence. A compactness argument, which will, in the end, just show us that the functions, well, in this case, the eigenvalues and the eigenfunctions converge to something, right? So in this, something which we don't know what it is, right? So in this case, for example, we can use the extremal characterization of the principal eigenvalue to obtain bounds. And this is quite classic. This is contained in the paper of Berestycki and others I mentioned earlier. Just substituting particular functions in the above formula. So that gives us a bound for the eigenvalues, and then to obtain, say, to show that the family U epsilon is pre-compact in some sense, we use classical elliptic estimates, Holder estimates, C alpha estimates, which depend only on the L infinity norm of the right-hand side of the solution. So since we are working with the normalization, here it is required the normalization that the L infinity norm of U is equal to 1. We already bounded the eigenvalue. We have, say, these C alpha estimates quite easily. Right? So the second part is harder, which is finding what relating somehow the limits. Well, these by limits I mean limits up to subsequence, right? The eigenvalue lambda epsilon and U epsilon converge to something up to subsequence, but we need to relate that something to the average problem. That is, say, the harder part. Okay, I'm gonna briefly go over this. The ideas behind that proof, which is a simplified version here in the, not in the paper, but here in the slides of the perturbed test function method from Evans, from one of the classic papers by Evans. Right? So the idea is that we take, say, the lim sub of lambda epsilon and an associated the limit of the associated eigenfunctions to a subsequence of eigenvalues which converge to that lim sub, and we look for an equation for it. Now, the way to look for equations for, in this case, an equation for bar U is to test in the sense of viscosity solutions. This is actually, this is a simplification of the actual argument, but an even greater simplification would be to assume, say, that everything is smooth, right? And since we have the convergence U epsilon tends to U, then we can sort of realize the ansatz I wrote on the board earlier, which is to say that U epsilon is equal to U plus epsilon squared times a certain solution of the cell problem, which is associated, say, in the simplest possible way to the limit function U. So, okay, in the let me say the formal definition of viscosity solutions, we sort of move the computations we want to make to on U, the derivatives on U, since we can't differentiate. We move that on to the smooth test function lambda, and see there we have something similar, var phi plus epsilon squared times U, something similar to the expansion I wrote earlier. Actually, this is quite similar to what I wanted to do on the board. We have these lower order terms, which we can somehow control, and pass to the limit using the continuity of the operator and find that U is a solution to the operator bar F. Right?
Is that a super or a sub solution?
Yeah, that's I'll leave it. Let's see, maximum. Yeah, that's a sub-solution. Here we have a convention, say the Laplacian is elliptic. So instead of minus the Laplacian, so that the inequality goes in the other way. Okay, so in the end, we find that U is a sub-solution for the operator and for that limit of eigenvalues, but then by the extremal characterization of the eigenvalue as the supremum of all such lambdas, we have an inequality between lambda, this bar lambda, which is just the limit of eigenvalues, and the actual eigenvalue of F, due to the characterization by Berestycki, Nirenberg and Varadhan. Of course, we can do that with the other limit, and we have equality for the eigenvalues, or convergence for the eigenvalues. Then the convergence for the eigenfunctions follows from the simplicity of these eigenvalues. In short, U should be a multiple of the actual eigenfunction, but since it's normalized, it has to be the eigenfunction. So first the eigenvalues, then the eigenfunctions. Okay, so I don't have much time. Let me just say that the proof of the rate of convergence is actually, I wasn't going to say too much about it because it's very intensive, say computationally. It depends on and actually a very interesting construction in the linear, well, actually linear and nonlinear case. A very interesting construction of, say, higher order correctors. So in that paper by Kim and Lee, we have a way of constructing like a better expansion. And in our case, we go up to, say, a third order corrector, W3. The second order corrector is the solution of the cell problem. So that sort of the same expansion you have from the beginning, from the ansatz, right? Which motivates the whole definition. But in their construction, you can go as high as you want. But to get the linear rate, I believe in the linear case, it is enough to go up to third order correctors, and you use those correctors to obtain an adequate, say, error estimate using this minimax formula for the eigenvalues due to Domesday and Varadhan, which is also a classic formula satisfied by the principal eigenvalue. And well, that would be all. Just to mention where we are in this line of research. We can the same methods more or less lead to a rate of convergence for the eigenvalues of nonlinear operators, fully nonlinear operators F, as long as they are sufficiently regular. Actually, very, very smooth, much smoother than in most homogenization applications. But that's what we have. And this is just via a linearization argument and using something similar to what we have in the linear case. And also for linear operators, we are close. We are fixing some problems, but we are close to obtaining a rate of convergence for the eigenfunctions using some of the ideas of Quesaban from variational setting through the use of like a nonlinear adjoint equation, a non-divergent form type of adjoint. And say that the most general case, say obtaining a rate of convergence for eigenfunctions for nonlinear operators, even for regular ones, is still out of reach. So that would be all. Thank you very much.
Yeah. Thank you. We have very from the room here, and then we go for the audience there. No?
Yes, very interesting talk, and maybe we can discuss tomorrow. So
of course.
Have more questions.
Yes, thank you.
Anybody wants to ask?
Question maybe.
Yeah.
Just, yeah. So I wanted to know this fully nonlinear operator. So, for example, if you look at the infinity Laplacian with some coefficient, do they form part of this class or they do not?
That's a good question. I'm not sure it's satisfied. I've never really worked with it. I'm not sure it's. I mean, in general, the notion of solution, everything applies, but I'm kind of not sure if it is uniformly lit. Does it satisfy the uniform elasticity
No,
condition?
I'm not so sure.
I'm a bit.
Maybe some singularity.
I'm a bit at a loss there.
Yeah. So it's somewhat degenerate. So not strictly elliptic kind of operator.
Yeah,
It's elliptic, but not like.
but not uniformly elliptic.
Yeah.
Okay, so yeah, I sort of remember that. So yes, that not in general for the homogenization approach, but here mainly due to the principal eigenvalue problem, we do need uniform ellipticity.
Yeah, I think for many things you don't need the uniform ellipticity. I think for your C alpha estimates,
Yeah.
it's important, but
Yeah.
otherwise I don't see many. The other things may go through.
Right. Well, no, of course. I mean, there's for say possibly degenerate equations.
Yeah.
There are many other references where the regularity theory comes from other terms.
Yeah.
Say for if the Hamiltonian, the dependence on the gradient is superlinear, for example. That's like another source of regularity where you can still use that to have convergence results. And compactness arguments and convergence, etc.
Any more questions from here? Anybody want to ask anything quickly? Because we have just 2 minutes.
Ravi, I want to ask.
Yeah, please go ahead.
Thank you, Professor Rodriguez, for a very wonderful lecture. Very clear, right from the introduction onwards. I have one question. You mentioned that presence results are done where epsilon does not depend on the slow variable x explicitly.
Yes.
What will happen if it depends on x? What are the difficulties?
The construction, at least the construction of these correctors, gets very, very complicated. It have coefficients which also depend on x. So these very say it's very concrete how you obtain them. You just sort of differentiate. That's why we need so much smoothness in the operator. It's sort of a recursive construction, an iteration procedure. And you differentiate, etc. And if you have dependence on both x and the fast variable, it gets very complicated.
Okay. Thank you.
Thank you.
Okay, so one more question, very fast, if anybody has. Because we are just running
30
out
seconds.
of time. 1 minute, one question. Oh, so we don't have. So let's stop the session for today here. Thank you, Andrea. It was really, I liked a lot. Thank you. Yeah, just say it. Okay.